Hello everyone, welcome to our Mathematical 1 lecture. And before talking about the topic, I wanna start by one situation. Have you ever seen that someone parking his or her car and someone comments like to the right or left and right there? Okay, that's the idea of being close. But not necessarily the exact, is the art of the limit in the mathematics. Actually, today I'm gonna talk about the neighborhood and the limit of sequence, as you see there. And when we say the neighborhood, what comes to our mind? Actually, it's somewhere which is near to our house, right? This idea is exactly the same in the mathematics. For example, let's take 2, right? Near the 2, we can count a lot of numbers. 2.1, 2.2, or 1.9, 1.8, right? Actually, by a definition to the neighborhood, we say that a neighborhood of the x0 with radius r is that all numbers whose distance is less than r. And we write it like this. And in the real line, we can show it like that. It's our x0, x0 plus r, and x0 minus r. These all our numbers. And in the mathematical way, we can also show it like that. Inside the curly braces, x0 is real number, such that x minus x0 is less than r. We can show the neighborhood of the x0 with two ideas. One of them is distance idea, another is tolerance. Distance idea says that x is the r units away from the x0, but tolerance states that smaller r means that more precise number intervals. For example, in there, our intervals are this, right? And we can also take smaller r, which gives us the more precise number intervals. And it's also convenient that take x0 as a positive and negative infinity. For example, we take the x0 as a positive and negative infinity, and with our endpoints, we need our endpoint, right? We can take an endpoint, for example, like that. For all a is more than 0, and we say that neighborhood of the positive infinity is endpoint a equals to from a to the positive infinity. And for all a is less than 0, which implies that minus a, the neighborhood of minus infinity is endpoint minus a, which equals to from minus infinity to minus a. And in the real line, we can show it like that. From a to the positive infinity, and from negative infinity to minus a. So, let's take the one expression in order to understand it more better. For example, n equals to 1 minus 1 over n, right? From this expression, we can see that as n goes to the infinity, positive infinity, or minus infinity, doesn't matter. Our fraction there, 1 over n, gets to 0. Gets close and close to 0. Now, it means our sequence will equal to 1. That's what that shows that the precise meaning of a limit. Actually, our fraction there can be 1 over 2, 1 over 3, 1 over 4, doesn't matter. It goes to very small numbers, and it's in the expression it will give us the numbers around 1. That's what I said. We showed the precise meaning of a limit. So our limits can diverge, converge, and we have indeterminate situations. For example, by a definition, we can express the convergence like that. For all epsilon is more than 0, there exists an epsilon is more than 0, such that f of x minus L, which is our limit, is less than epsilon. Let's look at one example. For example, 7n plus 1 divided by 3n squared plus 5n, and write their limit and goes to positive infinity. We can write this expression more simpler like that. And we can also show it like this. 7n over 3n squared. And n cancel. 7 divided by 3n. And as n goes to the positive infinity, our fraction equals to 0. And we can also prove this expression with this rule, definition. For example, we have this expression there, right? For example, 7n plus 1 divided by 3n squared plus 5 inside the absolute value is less than 0. Right? No. So, we can also express, as I said, like this. Right. So, can we also say 7 over 3 epsilon? Yes. So, that's what I said, an epsilon. Actually, it's a starting point of the convergence there. And graphically, I can show it. For example, it's an epsilon there, and an epsilon, plot epsilon, it's over L, right? It's like this. It intersects this line, right? It goes like this. As you see there, it is constant there. It means it converges. So, we have also another concept, which is divergence. The first limit can also, our sequence can diverge. And in this case, our situation a little bit different. For example, for all A is more than 0, there exists some B is more than 0, such that is more than A. For example, n equals to 2n, right? And as n goes to the positive infinity, our fraction 2n goes to the positive infinity. Now from this illustration, we simply say that it diverges. So we can also, as I said, we we can prove it by a definition. What is it there? Fx is more than a. 2n more than a, right? So, and from this, we can express like n is more than a over 2, right? So, which is our NA? Starting point of that divergence. Graphically, we can show it like that. L minus epsilon plus epsilon is our NA. Okay, it's our NA. So, intersects. Sorry. So it diverges like rockets goes to the sky, right? It goes to the universe. So as it is there, it diverges. So as I said, we have also situations that we have indeterminate forms. What's indeterminate form? It's neither of the convergence or divergence, none of them. We have an example that 1 plus 1 over n and n. If n is even number or if n is odd number, which implies that it's our fraction is 4k. There, in this case, our fraction is 0. So, we cannot say anything for this situation. We simply say that it's indeterminate. So, we can also ask that in the exercises we need to know whether this sequence diverges, converges, or indeterminate. To avoid this situation, we have the rule monotonicity. In monotonicity, we say that we just pay attention the subscripts of the A. For all A is more than 0, if n plus 1, an plus 1, and an plus 1 is more than an, so it means it's monotonely increasing. But we can also say that if an is more than an plus 1, it means it is decreasing. That's what helps us to avoid from indeterminate form cases. After covering the situations like convergence, divergence, and determinant, we can say some additional classifications. For example, bounded from above and not bounded. For example, we say that our sequence can convert some numbers, for example 2, right? For example, we have some number b, right? Which our sequence is bounded by b. And similarly, or in other case, as n goes to infinity, our an goes to infinity. Actually, it's not bounded from above, which means our function, our sequence, diverges. Now, as I said in the beginning of our lecture, we said that all these equations go to the number one, can go to the one number, special number, which is E, right? We also say is Euler number. For example, an 1 plus 1n, right? We can write this sequence and over n to the power of it, sorry. So, our n starts from 1, right? So, if our n is 1, it means our an is 2, right? So, if an equals to 2, 3, 4, 5, our method, they are bounded from below, bounded from above by 3. For example, put the number 3 instead of it. No, it's more better to take 4. 1, 4, and to the power of 4. Okay, after covering the bounded from above and not bounded, no, I just want to show you a very special number we have there, which is Euler number or Napier number. Actually, we can get some, sequence like 1 plus 1 over n to the power n. What would be if our n was 1, right? a1 equals to 2. So, according to the number, the sequence, as n goes to the positive infinity, our sequence is bounded from above by 3. So, and approximately, it makes our number, this situation leads to the creation of the number of E. So, as you see there, mathematics is so interesting, and we can see in different situations there, as I see in converge or diverge. For example, converge looks like one bird, right? Some birds fly some, height and goes in this, axis, look like this. But rockets goes like the function or sequence diverges, as you see there. And I want to end up this very special lecture here, and I want to say that I want to refer the Neumann expression that we don't learn the mathematics, we just adapt to mathematics by practice.